All right, let's get started. Get the lights adjusted. Okay, so a couple items of housekeeping. So number one, the notebook is going around. So go through it. If you're missing any, bless you, if you're missing any items, make sure that you indicate it on the sign-in sheet that's in the notebook. I just passed out homework 7 as well as the solution. I'm not really going to bother going through the solution since everybody did so well on it. It is what it is. So you all have the solution. You all have the homework assignment. You can go through that if necessary. Okay. Now, homework number 8 is due on Friday. Again, be cognizant of the schedule for the next couple weeks. You've got homework 8 due on Friday and homework 9 due the following Friday. I figured it's probably a good point or a good time to start mentioning the fact that we do have a final exam in here and make sure everybody's aware of the date. I don't know if you consider this lucky or not, but we drew, I guess, the last day of finals week for steel design. Your capstone presentation is the 28th. Well, if everybody wants a 0, we can cancel it if you want.
You said if nobody takes it, we all get 100. So
I'll get an A. It's not necessarily again. The amount of trust.
If he cancels it, none of us can take it.
Oh, if I cancel it, that just means everybody's getting 0. Well, I curve it to a 0. All right. Here, look. We'll discuss scheduling later. I want everybody to be aware of what the current schedule is. We're missing people today. So, if you want to have that discussion, we're going to have that discussion with everybody here, and everybody's not here. So, what? No, that's the deal. We'll discuss that later. Again, just be cognizant of homework 8 due on Friday. Yes, I did. What? We'll talk about it in concrete.
The last one was really pretty though. So I mean, uglier than the last one, still like like a 7 or an 8.
It's just a couple more squares.
We will talk about it in concrete design. Okay, everybody good? All right. So again, we're going to discuss a fair amount of mathematics today, so be ready for that. I've mentioned that before. So I actually want to begin our discussion here. All right, everybody, settle down, settle down. I want to begin our discussion here. So this is where we sort of left off last time, and this is a really good place to pick it up for our LTB derivation. So the first thing we had to do was just discuss torsion in general. Now, the general expression for torsion for a cross-section is GJ times the first derivative of twist minus ECW times the third derivative of twist. Now, if you're dealing with a circular cross-sections don't warp, so that second term just goes to 0, and it goes back to what you all learned in Engineering 216. However, if you are dealing with a cross-section that warps, like an I-section, then you've got to include your warping warping expression. When you look at I-beams in general, in terms of pure torsion, the ability to purely twist, I-beams are pretty flimsy. They get most of their torsional strength through warping. So if you don't include warping, you would have a fairly weak section. So you have to account for it because A, it's what's really going on, and B, it's where an I-section gets a lot of its strength. All right? Sound good? Okay, now, we're going to do a derivation of lateral torsional buckling, and I'm going to do my best to go over what I call the important aspects of math. I'm not expecting you all to recreate this derivation, and you have it right in front of you. So if I go a little fast, bear with me. But again, it's all there. There is something I want to be very clear in our derivation. When we perform our derivation, we're assuming that the beam looks something like this. So we have a beam, we'll say it's simply supported, and we'll say it's braced at its ends. So for simplicity, its unbraced length is equal to its span length. Okay? Now that's kind of important. What's really important is the loading. Okay? Now if you look at this beam, I'm assuming that this beam is subjected to equal and opposite end moments at the supports. Okay? Now if you draw the moment diagram for this type of beam, it's going to look something like this. So if I, go down, and I say, all right, it's time to draw the moment diagram. The moment diagram, goes up some moment, goes over, and goes down. In other words, this beam is subjected to a constant bending moment. Okay? That's really important for our derivation because we're going to be treating the moment like it's a constant. When you're dealing with constants in algebra, you can factor constants out. They're not variables, so they're pretty easy to deal with in that regards. That's also not true in a number of different loading scenarios. I mean, you all have seen the moment diagram for a simply supported beam subjected to a uniformly distributed load, and it doesn't look like that. Okay? So we are going to need to adjust our derivation to account for non-uniform bending. Okay? And we're going to do that adjustment through the use of a moment gradient modifier. So taking into account that moment changes. And we call that moment gradient modifier C sub B. So I would argue that of all the complications that will arise when you deal with lateral torsional buckling, C sub B is one of the big ones. So you'll want to pay attention to that when we get to it. Okay? But is everybody okay with this so far? Okay. Now what we're going to do is we're going to have three moment responses that we're going to have to consider, but in the end that's sort of splitting hairs. When I have this beam and I subject it to uniform bending, it's going to respond in three different fashions. First off, it's a beam subjected to load, so it's going to deflect downward. Okay? That's just how beams respond in general. So we're going to have a vertical deflection that we're going to have to consider. But also, since we're considering lateral torsional buckling, we're going to have a lateral deflection and we're going to have a twisting. So when you all see some of these equations, I want you to sort of understand where they're coming from. Now what I'm saying is that when you apply a bending moment to an I shape, again, part of the beam is in compression, part of it isn't. Okay? So there's this internal conflict. Part of the beam wants to buckle and part of it doesn't, and it responds by kicking out and twisting. Okay? So that's where that lateral torsional buckling comes into play. But also keep in mind that it is also deflecting downwards. Okay? Now, in terms of its downward deflection, in other words, deflecting in this y direction, if you will, we do know the differential equation for that. We know that the second derivative of deflection is negative m over EI. You all remember that from structural analysis. So I guess the first differential equation, or equation number one, that would describe this deflected shape is that the applied moment is negative EI times V double prime. Now we're not going to use that equation directly. I just wanted to show you that's a reminder of the fact that this is still a beam and it is still going to deflect like a beam. Now that's for its vertical deflection. For its lateral deflection, it's basically the same thing, that the applied moment is going to equal negative EI times the second derivative of deflection. A couple things are different. Number one, we're not dealing with EIX, we're dealing with EIY because we're not talking about the beam deflecting up and down, we're talking about it deflecting side to side. So it's deflecting about its minor axis, hence why we're using I sub y, not I sub x. Likewise with the deflection, I'm using V to represent deflection about the y-axis. I'm using U to represent deflection about the x-axis. As for the moment, it's not the moment, it's the trigonometric component of that, or the moment times the sine of that angle. And using small angle theory, we can say that the sine of phi and then phi are about the same thing, so we can keep that a little simple. So that's essentially, that equation is representing the lateral deflection, and for the most part it's the same thing as the equation representing the vertical deflection, just with a little bit of trig and notation change. So far so good? Now the beam is also twisting. Okay, so because the beam is also twisting, there is still the torsion equation, the one that we derived earlier, and that's that's one of the reasons why I wanted to spend a little bit of time and talk about torsion, so that when you see this equation, you go, where the heck did that come from? Now you know where it comes from. All right? Make sense? Everybody good? Okay. All right. Now, one of the things I'm going to do is use a little bit of trig to relate the amount of moment that's being applied at the ends to the amount of moment that's being applied in torsion. And you can go through and do the math. I know that's looked like a lot of vector stuff that you all saw in statics and dynamics, and I'm sure that you all I can see you're having a hard time containing your excitement over all of that, right? There we go. Now everybody see they're getting giddy. They're jumping out of their seats. It was a joke, not a very funny one. You can relate the amount of moment that's being applied in torsion to the slope of the beam, and the slope of the beam is represented by the first derivative of that deflection. So I can say that that torsional moment, that m sub z, that moment about the axis of the beam, remember the axis of the beam is going this way, so that torsional moment is basically related to the applied moment and the slope, the first derivative. So it's pretty straightforward. Okay, so far so good? So a little bit of plug and chug. I have the torsional response equation, and then I have that expression relating the applied moment to the amount of torsional moment in the section. Do a little bit of plugging and chugging, and I get this. And then to go from here to here, I just take the derivative again. Okay, so if you notice here, I've got a first derivative, and a third derivative, and here I've got a second, and a fourth. Okay. Now, the reason why that's important is because if you go back to equation 2 was related to the second derivative, so I needed that second derivative so I could plug and chug. So here's my expression right now. Plug in that second equation. Do a little bit of rearranging, and I get this. Okay, so this is a fourth order differential equation. Okay, love it, right? Good stuff. This is the fun stuff, right? So it's the fourth order differential equation. It's a fourth order equation in terms of the angle of twist. Okay, so this equation is representing the angle of twist along the beam, and it's basically saying that ECW times the fourth derivative minus GJ times the second derivative minus m squared over EI times the original function has got to be equal to 0. Now, I'll admit, that's a nasty equation. Okay? There's a lot going on. Okay? Now, there's 3 ways of solving this. I have 2 ways, but I guess the first way is Wolfram Alpha, right? Break out Google, right? But I do want to get a little bit mathematical. How many of you are in DiffEq right now? Okay, so some of you that are in DiffEq. For those of you that are in DiffEq, we could write a characteristic equation. We could say, you know, this is r to the 4th, this is r squared, and that's the constant, and then solve for your roots and plug and chug. We could do that, okay?
We barely got to the second order.
What? Wait, you're not...
That's not a joke.
Have you done Laplace transforms yet?
Just got to it last class.
Let's be honest, we really know.
Absolutely.
I'm learning more.
That's not a lie.
Okay, so all right, so a couple things. For those of you that are in the class, I have to believe you at least kind of know what I'm talking about, right? That you could write a characteristic equation, solve for your roots, and go from there. Okay, that. Oh. Okay. All right. Okay. All right. Hold on. That's the hard way of doing it. Let me explain the easy way of doing this problem. The easy way of doing this problem is to assume a solution that meets the boundary conditions and then ultimately solve from there. Now, if we go back to this, all right, so here's my beam, okay, and here's the deflected shape, or you can sort of think of that as the angle of twist, because it's going to the angle of twist function is going to kind of follow the same pattern, okay. Now, if I look at that function, okay, let's think about this, and let's use our noggins. Okay, so first off, I'm going to assume that based on my boundary conditions, because I've got it braced here and here, I'm going to assume that the angle of twist here and here is 0. Okay? Everybody all right with that? So that's point 1. Point 2. This is a simple support. Okay? What do you know about simple supports? What is true at a simple support? We know the deflection equals 0. What else do we know equals 0 at a simple support? Moments. Okay? So here's what I'm going to do for my solution. Okay? So the hard way would be to actually solve the equation. The easy way would be to assume an answer. This is what I'm going to assume is my answer, is this term right here. I'm going to choose a sine function. Now here's why I'm going to choose a sine function. Now it might seem like there's a lot on here, but I think you can sort of follow along with this. For instance, if I've got a sine function, what's the first derivative? The cosine, and then you go to negative sine, and then you go to negative cosine, then you go back to sine. Y'all remember that? Okay. Now, I've chosen this particular function for a very specific reason. If I plug in, let's look at this equation up top. Let's look at this. Okay? Let's look at that right there. What happens to that equation if I plug in z equals 0? What do I get for an angle of twist? I get the sine of 0, and I get 0, right? Now what happens if I plug in z equals L? What do I get? The sine of pi. And what's the sine of pi? 0, right? So this equation has 0 angle of twist at one end of the beam and at the other end of the beam. Make sense? Now, second derivative of deflection is going to be related to moment, right? Let's talk about the moment. So second derivative. Second derivative is this one right here. What happens if I plug in z equals 0? What do I get? What happens if I get z equals L? 0. Okay? That's why I've chosen this expression. And it might seem complicated, but there's a very specific reason why I've chosen a trig function, because all the derivatives are pretty simple, right? If you understand the chain rule, then it's pretty straightforward. Keep in mind that, they also repeat. Sine, cosine, negative cosine, then you're back to sine. Okay? So it makes life a little easier. Notice, look at this. The original function, the second derivative, and the fourth derivative all have signs, right? Well, look at my expression. Fourth derivative, second derivative, original function. The sign is just going to factor right out. Make sense? So here's what's happening, okay? So here's the expression. I'm plugging in. I know it looks messy, but it's literally just plugging and chugging, and I'm factoring out common elements. So if I take each one of these derivatives, factor it in, factoring out the common elements, I get this. Bless you. Keep in mind, by operating in this fashion, one of the things I'm assuming that's a constant is the moment, okay? I'm assuming that the moment is a constant. That's not always the case. In fact, most often than not, it's not the case. Okay? More often than not, it's not the case. So we've got to correct for that. And that's where this C sub B factor is going to come into play. Sound good? Okay. So here's what I've got. I've got this pile of junk times this pile of junk equals 0. You all remember middle school or whenever you learn this, if you got A times B equals 0, either A is 0 or B is 0, right? So I'm going to focus on what's going on inside the brackets, because ultimately I want to solve for the moment. The idea is how much moment is going to cause this thing to buckle. So take that term, solve for M, do a little bit of algebra. If it'll go for that, go right ahead. Solve for the moment, and here's what you get. Okay. Now, what I'm going to do is I'm going to take this expression. I'm going to take it and I'm going to rewrite it a little bit. The first thing I'm going to do is I'm going to write it in terms of stress. Okay, so instead of a critical buckling moment, I'm going to write it in terms of a critical buckling stress, so a moment divided by a section modulus. So take this, divide it by the section modulus. The second thing I'm going to do is a couple substitutions. All right, so I'm going to make a substitution for this warping constant. I'm going to make a substitution for some material parameters. I'm also going to make a few substitutions for these terms right here. So RTS. RTS is kind of like the radius of gyration for lateral torsional buckling. The reason why I'm making this substitution is so I kind of get an L over R term in there. Y'all remember L over R showing up for columns? It kind of shows up for beams as well. I'm also going to substitute this term right here, this H sub naught, and all H sub naught is the distance from center of flange to center of flange. That's all that is. And if you notice, that's in the lookup terms as well in table 1-1. Now, if you take this equation, plug all this stuff in, do a little bit of algebra, you arrive at this, okay? The 0.078 comes from the fact that if you take 2 times g, which is the shear modulus, divide it by pi squared times e, since these are your values, you get about 0.078. Go through and plug and chug, and that's what you'll get. That is the critical buckling equation for LTB, and that's it, okay? Everybody kind of follow along with that? I mean, you don't need to be solving fourth order differential equations for this. I really just wanted you to get a general idea of what's going on. Make sense? Now, real quick, I do want everybody to turn to table 1-1 just so everybody sees a couple things. If you notice, there's some new terms in this expression that you haven't seen before, like RTS and H sub naught. But if you notice in table 1-1, they're all there. See them over there on the right? Okay. Everybody okay with this? One of the other reasons that the equation is reformatted in this way, I mean, let's keep in mind, what's over here on the left on the bottom, what's over here on the right, they're the same equation. The reason why it was reformatted a little bit is because when you start doing some more advanced design, like everything that we did here, we assumed double symmetry, that the compression flange and the tension flange looked exactly the same. When they don't, and you have a singly symmetric section, the math gets a little more complicated. But if you go through and derive the expressions, bless you, what you'll find is that the equation for singly symmetric sections looks kind of like this. So the idea was, well, let's make the doubly symmetric sections look kind of the same so that when you get out of here and you're doing more complex design, the equation seems somewhat familiar and it's not as daunting. That was sort of the whole point. Everybody okay with this? No. No. But, I mean, you could write it down if you want. You won't use it, though. Everybody good? Now, if you go to chapter F, and now I want everybody to turn to chapter F. I want to make sure everybody can find this. F. Remember, chapter E was where all the column stuff was. Chapter D, shear lag, all that. I want to go to chapter F. And specifically, I want to go to section F2. You're way far ahead. That's chapter D. So, like a few pages.
Doubly symmetric compact.
Hold on. I got to get mine. I want to make sure everybody's finding this. F2. Now, if you look on the previous page, you'll see that table user note, like at the very beginning of chapter F. It'll tell you we're in F2 because we're dealing with a cross-section that's an I shape, and we're ultimately going to be dealing with compact sections. Now, I'm on page 16.1-47, okay? Is everybody with me on that? Now, if you look at the bottom, you can see that equation, F2-4. Does everybody see that? That's essentially, for the most part, the same thing we just derived, with a couple minor exceptions, okay? First one is if you notice under the square root, instead of J over SXH naught, it's JC over SSH naught. The C is just a modification factor for if you're dealing with a channel as opposed to an I shape. So that's not going to matter for us. We're just going to take it to be 1. But then there's that C sub B, okay? And if you notice, that C sub B pops up not only in the equations above F2-4, but it pops up all throughout chapter F. It pops up quite a bit, okay? Does everybody kind of see that? This term right here, okay? So what's going on with C sub B? Okay, and don't worry, we're going to have an example on C sub B, okay? When we did that derivation just now, it seemed kind of, let's just factor it out, but it was actually sort of a big connotation to that. We just sort of factored the moment out as if it was a constant, okay? And that's not the case. If we had treated the moment as if it was a variable, instead of moment equals constant, if moment was a function of z, function of the length, that equation would have gotten really tough. Okay? If you thought that was tough, that was nothing compared to if moment was a function. That would have gotten bad. Okay? So we adjust that solution for non-uniform moments through the use of C sub b. Okay? So I can see it right now. What do we use C sub b for? Oh, it's a factor of safety. No. 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 It's actually the exact opposite. C sub b serves to increase your capacity, not decrease it. Okay? Okay? It actually works the opposite way a factor of safety does. Not quite. Not quite. It's not a factor. No. Let me explain why C sub b is necessary. That's a first. I've never heard factor of danger. It's not a matter of conservatism. It's a matter of reflecting reality. And let me explain. Okay? So go back to what I was saying earlier. If you have a section that is subjected to uniform bending, that's what the moment diagram looks like. Okay? Now look over on the right. That is a very, very typical loading scenario. And the moment diagram looks as follows. Everybody okay with that? Now here's the problem. Okay? When you make this assumption, okay, what you are saying is that every single cross section, every single samurai sword cut throughout the beam must be able to attain its full capacity. That's not true, though, in most scenarios. If I look over here on the right, I don't need to develop the full strength right here or here or here. I only need to be able to develop the full strength right there. That's where the beam needs to be able to develop its full capacity, not everywhere else. Okay? So by not incorporating C sub b, or in other words, taking C sub b to equal 1, what you're doing is unfairly penalizing the beam by assuming that the beam is subjected to a load that's not realistic. Okay? Does that make sense? C sub b definitely needs to be accounted for. Now, C sub b values tend to range from anywhere from 1.0 to, 2 or something like that. So don't think that the C sub b values get a little ridiculous. But they do need to be accounted for because they do need to reflect reality and what's really going on with the given cross-section. All right? Sound good? Okay. Now, one thing I'll point out, a couple things. Oh, that's exactly what I was saying just now. So the first point on this slide was literally what I was just saying, that if you assume that the moment is constant, you're saying every point has to reach M critical, which is not the case. All right. One of the issues, though, with trying to account for non-uniform moment is if we tried to derive a C sub b for every single conceivable moment diagram, C sub b would get a little nuts and it would get a little complicated. So what the spec does is it uses an empirical expression as follows. Okay? So this is, if you all are on 16.1-47, you'll see this equation on 16.1-46 right there on the left. Okay? Now, you've seen your design folks, I'll tell you that this C sub b expression is a little easier than the one for bridges, okay? Because I find it to be a little easier because it sort of takes all the sign convention stuff out of the way and it makes it a little easier to deal with. That's my opinion. But we'll get to that next semester. Now the C sub b for building members is 12.5 times M max divided by 2.5 M max plus 3 MA plus 4 MB plus 3 MC. And we'll explain how you go about getting those here in a little bit. But a couple things to point out. Number one, the nice thing about this expression is all of the moments are taken as absolute values. So whether or not your moment diagram is positive or negative, you're taking the absolute value of the moment. So if you have a segment that goes from positive to negative moment, you would still take absolute values. Okay? Sound good? Second, what you do is this. So if you've got some, let's keep this simple. Okay, so let's say you have a beam that looks like this. Okay, and let's say it's got a distributed load on it. There's a reason why I'm redrawing this. And let's say you have braces framing in here, here, here. Okay, now if this beam is L long, how long is its unbraced length? The beam is L long. How long is its unbraced length? L over 2. Okay, so here's how this works. Would you agree that the moment diagram looks something like this? Sound good? Okay, so here's what you do. When you compute C sub B, you take each individual segment one at a time. So I'm going to look at the segment on the left and the segment on the right. Now, since the segment on the left and the segment on the right are the same, I can just look at one of them in this instance. What I do is I take this moment diagram and I split it up into quarter points. So that means just, something like that, and something like that. Sound good? So in that instance, this would be MA, this would be MB, this would be MC. Sound good? It doesn't matter if you go left or you go right. In other words, that could be M sub A and that could be M sub C. It doesn't matter because if you look at the equation, they're treated the same. Okay? M sub max is the absolute largest moment seen within a given unbraced length. So that moment is going to be right here, M max. Sound good? Now that is for this shape, for this cross section. Over here, where all I have are braces, if the length and the unbraced length are the same, then all I have are braces here and here, right? So if I look at that moment diagram, what I would have is something like here's MA, here's MB, here's MC, and that is MB and M max. Does that make sense? Everybody okay with that? So you need to make sure that you're able to differentiate between what is the length of the beam and what is the unbraced length of the beam. That's really important, okay? Make sense? That's really important. This beam, like this beam here and this beam here, are going to have different C sub B values. This one over here on the right, I believe if I remember correctly, the C sub B is 1.67. Let me see. Or no, sorry. This C sub B value ends up being 1.3. This one ends up being 1.14. So I was getting that mixed up with point loads. All right. Everybody okay with this? Everybody good? What's that? What about that? You just plug in the same values here. I mean, that's basically it. You just plug in the same values. What I want you to recognize is the fact that they can be the same. Does that make sense? All right. Is everybody okay with that? Okay. If you're okay with that, then I want you to look at the following beam. So this beam is a little more complicated, but if you're okay with this, then I think you'll be able to assess this. So this, yes?
So C sub B all it's doing is helping us not do math, other math?
Basically, yes. It's making really, really complicated math really simple, in a nutshell. Sound good? Okay. Now, this problem that we're about to do right here is really going to break out your structural analysis skills, okay? Because this is going to be a lot of cutting sections and summing moments. I'm going to skip a lot of that but you need to be able to do that, okay? So if you've got a beam that's got a really complicated loading, gone are the days of just WL squared over 8 and all that. You've got to break out the sum of forces and sum of moments and do some actual work. So just make sure that you're aware of that. Now I have a beam that is subjected to a 40 kip load at B and then a distributed load of 3 kips per foot between B and D. All of these loads are factored, so we're okay with that. And lateral bracing is provided at A, B, C, and D. So this beam the beam itself is 45 foot long, right? How many unbraced segments do you have? 3. So you should have 3 different C sub B values, 1 for each segment. It's kind of like a column. You would take each segment and evaluate it individually. Okay? Sound good? All right, so let's see where we can get with this problem. Okay, while my little notebook is loading up. Okay. Okay. I'm lazy. What, is it 21 or 22? 22. Okay. Now, so the first thing that you would need to do is draw the moment diagram. Now, I'm going to make this somewhat fast and somewhat simple, but I want to make sure everybody's aware of what's going on. All right, let's see if you all can remember your structural analysis patterns and skills. So if I wanted to draw the moment diagram, the first thing I would need to do is find the reactions, and then after that, what do I do? Shear diagram, then the moment diagram. So let's see if you all can recognize some patterns. I'm going to have a point load right here and a point load right here, right? So what is the shear diagram? What's the shear diagram going to look like from A to B? Constant. Yep. Yeah, up, over, and down. So what's the moment diagram going to look like from A to B? Linear, right? Now, what I'm saying is that when you go through and do the math, you get a moment diagram that goes like this, and it goes linearly from 0 to 300, okay? Okay. Now, well, I'm skipping it. I'm skipping all that. You can do it if you want. I'm saying solve for the reactions, draw the shear diagram, then draw the moment diagram. I'm telling you that'll be 300. Yeah. We can do it. Actually, you should do it. No, I mean, what I'm getting at is you really should. Because, you know, you want to make sure that you're comfortable with this stuff later on. Sound good? Okay, now, what is the shear diagram going to look like from B to C and from C to D, I guess I should say? The shear diagram will be linear, so the moment diagram will be parabolic, right? Okay. So what I propose that it looks like is this. Let me see how I'm going to do that. Oh. That ends up going down. Man, that was horrible. There's a particular value I'm trying to get, so That's a little better. All right. This value ends up going down to about minus 337.5 when you go through and do the math. And then over here, it gets brought back up to 0. Okay? I mean, is everybody okay with this, or do I really need to go through and do the math? You can do that? Okay. Okay. All right. Now let's do some intermediate calcs. Let's first off go to segment AB. Now if segment AB is linear, help me out. If it's linear, then what is AB, or what are the quarter point moments going to be if it's linear? You have calculators? My goodness. What's that? There we go. 75, 150, and 225. Everybody okay with that? Now, how about let's skip ahead to segment C sub D. How are we going to find that, and that? There we go. Somebody's remembering them structural analysis skills. Why don't we do this? Why don't we look at C sub D, or segment CD, as if it is a segment with a distributed load, 3 kips per foot. This distance is x. And that's m, and m of x is minus 3 over 2x squared. Y'all remember that? The load is 3 times x, moment arm x over 2. Bringing it back, right? Bringing it back. All right? So what do we get for each of these segments? I want you all to tell me. What do you get for here, here, and here? Do you all remember this? Am I going too fast? No, that's fine. That's fine. That's for the middle one. So we'll just say minus 84.4. Now what about for the other two? Negative 21.1 is right here. And what about this one? Anybody? There we go. All right. Now that's this. If you go through and do the center segment, and I strongly encourage you to do this. I'm serious. You're going to get, let's see, you're going to get 203.9. You're going to get 65.6. And you're going to get minus 114.8. All right? Sound good? Now, we're going to very, very quickly finish this problem next time, but I do want everybody to follow along with me on a couple things. Okay? What is M max for this AB segment? No, right there. That's important. We're not talking about M max for the beam. We're talking about M max for each segment. This is really important. What's M max for this segment? What's M max for this segment? No. All absolute values, 337.5. Okay? They're all absolute values. What is M max for this segment? 337.5. Okay? MA, MB, MC, 75, 150, 225. Over here on the right, 21.1, 84.4, 189.8. All positive values. Over here, 203.9, 65.6, 114.8, positive. Okay? No negative values. Okay? If you understand that, you can plug and chug into that expression and get all of these. Okay? I encourage you to do that sometime between now and Wednesday. But we will close that up on Wednesday, and then we will get into LTB. Sound good? All right. That's all I've got. I will see you all either on Wednesday or in a few minutes.